Okay, so last time we talked about algebraic sets um, in an affine n space. So we defined affine n space to be n tuples of elements in the field. So you should think of it as for instance, affine plane would be like a plane with xy axis. Yeah. So n-dimensional affine space is just an affine space with n directions, so to speak. Yeah. And as a set, it's just k power n. But since we don't really think of it as vector space, so there is no addition, multiplication kind of thing going on. We should think of elements of the set as points. We denote it by a and k. Yeah, or sometimes just en when k is understood. Yeah, affine n space. And algebraic set in an affine n space is a zero set of some collection of polynomials in kx1 to xn. Yeah, so if you have a polynomial in n variables and you look at its zero set, that means n tuples such that the polynomial vanish on that n tuple. Then that set is called an algebraic set. So simultaneous zeros of elements of S. Or they are called affine algebraic sets in A and Q. And we saw that zero set of a subset of some polynomial polynomial ring is same as the zero set of the ideal generated by S. Yeah. And we also defined an operation in this. So given an ideal in the polynomial ring, you can associate a zero set in the affine n space, and which is an algebraic set. Now, given any subset of affine n space, you can define an ideal. Yeah, so X is some subset of A and K. Then you can define an ideal. You can define this collection F such that FA vanishes for all A in X. And then you can check that this is an ideal, because if F and G both vanish at all points of A, then their sum will vanish. And if G is some element of the ring kx1 to kxn and F vanishes at all elements of A in X, then of course G times F will also vanish. Yeah, so this is indeed an ideal. And then we saw some basic properties. So if I is contained in J, ideals of kx1 to xn, then a zero set of I contains zero set of J. So it's inclusion reversing zero set, and so is this ideal. So if X is contained in Y are subsets of A and K, then IX contains IY. And then we saw that if we take two ideals, I and J, and take their sum, the zero set of that is the intersection of zero set of I intersection zero set of J. And this is sort of straightforward. Yeah. So this intersection, which is same as zero set of I union J. So this is more or less a straightforward tautology. And then this proof we saw that zero set of I times J for two ideals I and J. So in these steps, I and J are ideals of IJ, ideals in some polynomial ring kx1 to xn. I should have made it smaller. In kx1 to xn. Or maybe in all this. Okay. And we know that the zero set of an ideal and the zero set of radical of that ideal are same. Yeah. So from zero set you can't make out you can make out the ideal only up to radical in some sense. You can't pick out the ideal completely. So the ideal and so two ideals which have the same radical will have the same zero set as well. And then we saw that ideal of zero set of ideal of definition of zero set of an ideal J in kx1 to xn is contains the radical of J. And I also told you that though we didn't see the proof, that equality holds, and that's a little more difficult. So that's by Hilbert Nullstellensatz, whose statement and proof we'll see later. So technically there is an equality, but we only indeed there is an equality, but we only have seen a proof of one inclusion. Yeah, the other inclusion is difficult. So one could ask, what about the other? So what if I start with an algebra with a subset of A and K and ask whether this equality hold? Z of ideal zero set of ideal of X, is it equal to ideal of X? So what's the answer? Does the equality hold?
No, it doesn't.
So that's a counter example.
So if X is affine algebraic set, then it's fine.
Yeah, so the problem is if I take arbitrary algebraic set, it won't work because zero set of I of X has to be an algebraic set. Yeah, so if I take arbitrary subset, it won't work. So for instance, if I take graph of sin X or something like that, yeah, then it won't work because it's not an algebraic set. Or if I take so in some interval, for instance, so in A1, if I take some interval A1 C, let's say, I take something which so some infinite set, in fact, yeah, then it won't work. So so the only way it can since the left hand side has to be an algebraic set, the only way this equality can possibly hold is when it is an algebraic set. So yes, if X is algebraic, otherwise it can't hold. Right, so let's just see this. So we have to prove this equality. So let's take something in the right hand side. We'll show that it's in the left hand side. So let's take a n tuple A which lies in X, and F. So if F belongs to Ix, that means F of A has to be 0. Yeah, for all. So this is true for all A in X. Yeah. So only those F belongs to Ix for which F of A is 0 for all A in X. So in particular, F A is 0, but if F of A is 0, this implies A belongs. So this is true for all F in Ix. Yeah, F of A is 0. So that tells you that A has to be in the 0 set of I of X. Yeah? So we get this X is contained in 0 set of I of X. Yeah? So that's one inclusion, and then you have to prove the other inclusion. So so for the other inclusion, so here we didn't really use that X in an algebraic set. So for other inclusion, we'll use the fact that it's an algebraic set. So X. So what happens is if you do this Z of I of X for some arbitrary X, what you get is basically, so we gave a topology, remember, on the affine space. So what you'll get is the closure of X in the topological sense. Yeah? So remember, we gave the topology to be all closed subsets are algebraic subsets. Yeah? So if you take closure of X, then you get Z of I of X. Okay, so anyway, let's just show that if X is an algebraic set, then we have equality. So if there exists, so X is an algebraic set means there exists J such that X is equal to 0 set of J. I is X, that is X is an affine algebraic set. Then what is I of X? I of X is I of Z of J And this we have already shown, it contains the radical of J. Yeah. So from this step here, we know that this contains radical of J, and then we apply this inclusion reversing property. So zero set of I of X will then be contained in zero set of radical of J, but that is same as zero set of J, yeah, which is X. So we get the other inclusion as well. Okay. So this identity, if X is an algebraic set, is okay. It doesn't require any big result as well, like Hilbert-Nernst. This is a straightforward. So we are for this inclusion, we don't use Hilbert-Nernst answer. This is so actually like some manipulation, yeah. So theoretic manipulation about some basic. Any questions so far? Okay, so let's continue. So this was most, except for the last one, mostly from last time. So oh, I hadn't talked about algebraic Zariski topology on a affine space. Yeah. Okay. So maybe somehow I thought I did talk about. Okay. So I had prepared the notes, and maybe that's what was in my memory. So Zariski topology on affine space. So we want to give a topology on affine space, and the topology, as I said, is you declare algebraic subsets of A and K are closed. Okay. So the collection of closed subsets are all affine algebraic sets. So one has to check that this does give a topology on affine space. Yeah. So that means you have to check that empty set is there, whole set is there, and since you are looking at, so instead of giving open set, I'm giving you closed sets. So then you have to check that not arbitrary union, but is closed under arbitrary intersection and is closed under finite union. Yeah. If we were giving open sets, then we would have to check empty set, whole set, and is closed under arbitrary union and closed under finite intersection. But since we are declaring what are the closed sets, we have to check something slightly different. Yeah, everyone remembers the topology, right? It hasn't been too far away. Yeah, so we had so since I taught you guys, it's not too far away. Yeah. So let's check. So of course, if you take the zero set of the constant term, constant element 1 or any unit for that matter, then the zero set is empty. So the empty set is a affine algebraic set. Hence, empty set is closed. And if you take the zero set of the zero polynomial, then you get the whole affine space. So the whole set is also closed. Yeah, the whole of affine space is also closed. And then for finite union of algebraic sets are algebraic, we use this identity. Yeah, so Z of I intersection J is same as Zi union Zj. Yeah, so once you do it for 2, then finite is just inductive. Yeah, or you can do it at one go. If you have finitely many algebraic sets given by ideals I1, I2, In, then you just take the intersection of these ideals and look at its zero set. You'll get you'll get an algebraic set, which and this will be union of the given algebraic sets. So it's closed under finite union, and for arbitrary intersection, we'll use the other one. Zi intersection Zj is Z of I union J, But this you can do it for arbitrary collection. You don't have to do it for finite. Yeah. So let X alpha be z of I alpha, alpha in some indexing set omega, and I alpha, maybe I should have written here, I alpha is contained in kx1 to xn ideals. Okay, so yeah, sorry. Okay. Then intersection of x alpha, alpha in omega is same as zero set of zero set of union of I alpha, alpha in omega, or you can take the ideal generated by them. Okay, so this identity is so if you do the proof of this thing, the same proof goes through here. Easy, so straightforward. So one direction, one inclusion is okay. You just because you know the union of I alpha, each of them contains I alpha. So the zero set of this will contain. So I alpha is contained in these unions. So zero set of I alpha will contain. Okay, so maybe since we are yeah, so I don't know. Do you want me to do this? So let's just do it. Yeah. So I think the space should be enough to do it. So let's take A in intersection X alpha, alpha in omega. This implies that since A belongs to X alpha for all X alpha, that means FA is 0 for all F in I alpha. Yeah, so A belongs to X alpha means and X alpha is 0 set of I alpha means for every F in I alpha, F of A is 0. Yeah, so Fa is 0 for all F in I alpha, and since this holds for all alpha, so for all F in I alpha and for all alpha in omega. Yeah, this is what you get. So this tells you that this implies. So this immediately implies that A belongs to 0 set of union of I alpha, alpha in omega. Yeah. So since it vanishes for all polynomials in this union, so we have one inclusion, and for the other inclusion, if A belongs to 0 set of union of I alpha, alpha in omega, then yeah, so union, so this of course is, so this is contained in the, of course, Z of union alpha in omega I alpha is contained in Z of I alpha for all alpha in omega, because the union is a bigger set than this one. So the inclusion reversing tells you this holds, which implies Z of union of I alpha, alpha in omega. is contained in the intersection of these guys. So Z of I alpha is same as X alpha alpha in omega. Okay, so you get both inclusions. Is that okay? Yeah. So we get both inclusions. So you have this identity. So it's closed under arbitrary intersections. Yeah. So it is indeed a topology. So that proves that this is a topology, and this is called the Zariski topology. Hence, this is a topology on NK. I should have just erased this part. So we'll and it is called the Zariski topology. Zariski topology on ANK. So it's quite different from the regular topology you have seen on nice. So even if K is C, so you have to take K as an algebraically closed set. Yeah. So then only, then only most. So these definitions, as I said, many of these definitions work. So again, this will give you a topology and all, but some results may not work. Okay. So this is a Zariski topology on A and K. So maybe I'll start the example from here. Okay. So so let's just analyze what this topology is. So example A1K. Yeah. So in A1K, what or maybe let's just fix K to be C. Yeah. So that we can compare with. So A1C is same as C. Yeah. And there is a topology we are familiar with on C. Yeah. So it's a topology coming from R2. Yeah. So what is what is the Zariski topology on A1C? So what is the Zariski topology? On A1C. So what are the first by definition we can first figure out what are the closed sets. So what is an example of of course empty set and C are obviously closed because it's a topology, but in general what are the closed sets in A1C? So what are the algebraic subsets of A1C? Those are the closed sets. So what are examples of algebraic subsets?
Yeah, finite set of points, right?
Yeah. So it has to be zero set of some polynomial. Yeah. So now the polynomial is so it's finite set of points. But why? So now the polynomial, which kind of polynomials we can take in which ring? It's Cx. Yeah, just one variable. Cx1 or just Cx. Yeah. So fx is some polynomial in Cx, then or some collection of polynomials maybe. Yeah. So then I should put subset. But you can, in this case, you can say one polynomial because then let's say S, then X is a zero set of some S, but S are ideal generated by S. So in this case, it's going to be some ideal in CX. So in fact, you can say, since you are in a PID, it's actually ideal generated by some polynomial. Yeah. And zero set of a polynomial in CX. So if you are given a polynomial in CX, it splits into linear terms, yeah, linear factors, and there are only finitely many linear factors. So X is set of zeros of fx, which is finite. So, topology on A1C is in the language in the terminology of which we learned in topology class, it's cofinite topology. Yeah. So we know that this is coarser than the usual topology on C. Yeah, the Euclidean topology on C. So it is quite different. This is not. This is far from. This is not. For instance, this is not Hausdorff. Yeah. So things to know about this topology is that as a topological object, this is very bad. So in fact, if you take any two non-empty open set, they will always intersect. So it's non-Hausdorff in a very bad way. So any non-empty open set is in fact dense in A1C. So this is what happens in A1C, but there is some sort of good news as well. So now if you look at A to C, which is C cross C or C2 if you like, yeah. So the topology here on A to C is not the product topology. Otherwise, we will be in really big trouble. Yeah. Then it will be closed sets will be really limited. Yeah, only finite sets, cross finite sets. Okay. So other than the whole set, that is. But here in A to C, what are the closed sets? Or maybe this time, what are the open sets in Zariski topology? Or maybe let's just forget about open sets. So we know what open set. Once we know what closed sets are, open sets are just complements of those. So open set in the previous example in A1C is complement of finite sets. Yeah. So of course, finite collection of points is going to be closed in A to C. Why is that? Okay, let's try to figure out what are the closed sets. So what are the examples of closed sets in A to C? So again, algebraic sets. So what kind of algebraic sets we can get in C2? Give me, so let me pause this. I'll have to. Pause. Let's continue. So what are the closed sets in Zariski topology? In A to C. So some examples are, so you can take a zero set of some polynomial. Yeah. So if and now the polynomial happens to be in Cxy. Yeah. So instead of writing x1, x2, I'll write Cxy. So f is some polynomial in Cxy, then zero set of this f. So f can look like something like x square plus y or something like this. Yeah. Minus 1, x square plus y square minus 1, something like a circle. Yeah, so it's sort of difficult to picture because I've taken C, but you can think of the real picture. So it's like so complement of a circle, for instance, and so on. Yeah, so complement of curves complex complex dimension 1 objects in C2. Yeah, those are open or complex. So zero set of such polynomials are closed sets. But these are not all. I mean, I've taken zero set of only one polynomial. If I take zero set of two or more polynomial, then I can get some smaller sets as well. So in fact, what I say is every finite set. So these are there. Every finite set is there. Is closed. And so on. Yeah, so zero set of some point. So you see that there are more closed sets than just the one you will get by taking the product topology from A1C cross A1C. Yeah, so it's the topology on A2C is not the product topology induced from A1C. Yeah, but how do you see that every finite set is closed? So for this, you just have to check that every point is closed. Yeah, because finite union of closed sets are closed. So you want so how does this? So you take a point in C2. Let's say A comma B belongs to C2. Then how do you show that this is a closed set? This is zero set of which collection of polynomials?
X minus A and Y minus B.
Yeah, so you take X minus A comma Y minus B. If you like, you can take the ideal generated by this. So this, remember, is a maximal ideal, and zero set of this is precisely A comma B. Yeah, it's exactly this. Okay, so you get 1 point, and then if you want many points, then you just take the intersection of these ideals and such ideals. So any finite set you can get this way. Okay, so that's how, this is how. So again, if you go further one dimension, you get more and more closed sets. So it's never a Zariski kind of. It's never a product kind of topology. Yeah? So it's much more interesting than the product topology. Okay. Okay. So now, yeah, let's. So we'll go towards this affine. I want to define affine variety. So for that, we need something called irreducible algebraic set. So an algebraic set X in. So you can read, right? It's big enough.
Yeah, it's okay.
It's okay. Yeah. So an algebraic set X in AN is said to be irreducible if it is not reducible. And what does reducible means? So if you can't write it as union of two proper algebraic subsets. Okay. So if you can't write X as X1 union X2, where X1 and X2 are proper subsets of X and they are also algebraic in AN, then you say that X is is an irreducible algebraic set. If you can write it, then X is reducible. Okay. So for example, this one is the first one is reducible. Yeah. How about the second one? Is it reducible or irreducible? So from the picture, you can figure out that whether this is reducible. I mean, this is a parabola and a line. Yeah, so you can write it as union of these two. How about the second one? So this is just one guy. Yeah, so this is irreducible. Whatever the equation is, so you can't really break it apart in some sense. Yeah. You can't write it as union of two proper algebraic subsets. And third one is again.
No, exactly. How do you get that from the picture? I mean, sort of.
So this the first one you can write it as union of.
No, I mean the second one. Second one.
So there is only one object, yeah. How do you break it, sort of? So we'll make this more formal in terms of ideals and stuff. But the point is that there are no sort of so there is no way you can't break it in some sense, yeah, into reducible components. There is no so if you take an maybe this is the better. So if you take an algebraic subset which is properly contained in this guy, then it has to be a sort of points. Yeah, you can't get a big chunk out of it. Yeah, so you can't write it as union of two algebraic subsets. Okay. So how I mean.
No, maybe you can take out a circle from the left and one cubic from the right.
Circle. This is not a circle. This is some. So this is equation of one polynomial, if you like. Yeah. So maybe.
Yeah. So if you write down the equation, then it's.
Yeah.
Then we can find out. Yeah.
Yeah. So, so I mean, from the picture, what I meant was this. This looks like an equation of one polynomial. It's not. I haven't drawn this as circle or something. Yeah, just drawn like this. So x square minus y square plus y cube, something like this will give you this equation. Something. Okay. So so this I mean, and then one has to argue why the zero set of this is why this leads to irreducible thing. But maybe I'll do that, but later. But from the picture, meaning if you don't see obvious irreducible reducible component, that means it's irreducible. Yeah. And number 3, you can see two irreducible component. One is a plane and one is a line, and they're all these two are the two reducible components. So this is reducible. So the middle guy is irreducible, the others are reducible. Now you can take a line that will also be irreducible. So something which you can't somehow. So this will be given by some polynomial. If you want some algebraic subset of it, then the ideal defining that algebraic subset is going to be a bigger ideal. Yeah, so it has to contain the first ideal. So somehow from there you can somehow argue. But we'll make an algebraic. We'll make a algebraic statement, and then it will be easier to verify. Okay, but one should also have pictures in mind. Yeah, so this is that's why pictures. I mean, that's what will give you intuition. And of course, proofs, when you write, you have to write it using algebra. Okay. So so first thing to note is that if you have an irreducible subset, yeah, algebraic set, then X is an irreducible algebraic set, then X is connected. Okay, so this, for instance, in picture 2, you can see it is connected. This is connected. In fact, in all of them are connected, but of course you can get algebraic sets which you can get. But the converse is not true. Every connected set is irreducible. Is always is obviously false. Yeah. So this one is reducible and connected. Yeah. So only one direction is true. So irreducible algebraic sets are connected, but connected doesn't imply irreducible. Okay, and when I say connected, it means in the subspace topology. So this set is so in this algebraic set, you can give a subspace topology, and in that topology, this topological space is connected. Okay, but for this, see, you need for this K to be an algebraically closed field. Okay. So it doesn't work if K is not algebraically closed. Can you give an example before we get to a proof? Example of an irreducible algebraic set, which is, yeah, I think this is it.
Yeah, so sorry, exactly what do you want? Can you say again?
So over non-algebraically closed, so you can talk about affine and space over reals. Yeah. Does irreducible imply connected? So topology, etc., you can define the same way. Yeah.
No, over the reals you could look at some elliptic curve, right?
Yeah. So for instance, we drew the picture of elliptic curve, and you saw there were two components. Yeah. And you remember this cofinite topology is coarser. So if it is disconnected in a finite topology, it's obviously disconnected. Yeah. So is it? No. So how do I say it's disconnected in the Zariski topology? So it's not disconnected in the, yeah. Yeah. So. Yeah, it's a bit difficult. So yeah, here the picture. That's why I got a bit about it. Yeah. So in Zariski topology, you can't write it as an algebra. Yeah. So meaning it's not connected. So here it is connected in the classical topology as well. Yeah. But if you put R here, then it won't be connected in the classical topology. Zariski topology is a bit.
So you can sort of break up a elliptic into two zero-set of polynomial, right?
No, that you can't do. Yeah, that is what I'm trying to say.
Oh, you can't do. Oh, okay.
Yeah, no, can't do. So maybe in the Zariski topology is still okay, but pictorially it gives you a different intuition. Yeah. So the elliptic curve, or for that matter, you take a hyperbola. Yeah, it has two components, connected components. If you think in terms of classical topology, but I don't think you can break it up in an algebraic way. Okay. So there is something. Yeah. So there is good reason for it, but so you can look at instead of looking at points, you can look at what is called M-spec, spectrum of maximal ideals, and there, of course, it becomes connected, and maybe the reflection is good enough. Yeah. So I don't think you can break it up. Okay, but what I meant was pictorially it gives you a different answer. Yeah. So if you take K to be R, then the picture of elliptic curve from last class or last to last class, you saw it had two components, or you can look at hyperbola for that matter. It has two components, but it's sort of irreducible. Okay. So it is irreducible, but not connected in the classical topology. In Zariski topology, connectedness is a bit visually, it's a bit painful to look at. Yeah. So this, I think this argument will go through even in for non-algebraically closed field, as long as you are looking at a connected with respect to Zariski topology. Okay. So let's just prove this, that irreducible algebraic set is connected. So suppose you can write, so we'll do a contradiction. So suppose X is disconnected, then we will show that it is reducible. Yeah. So suppose you can write X as U1 union U2, where U1 and U2 are disjoint proper open subsets of X. Yeah. But X is given the subspace topology. So you can write UI as VI intersection X. And sorry, my daughter has been interrupting me, so I'm a bit distracted. This, okay, so UI is VI intersection X, and VI is an open set in A and K. Right, so we want to write it as a union of two proper. So we want to show that X is reducible. So what you do is consider Zi to be this closed subset An minus Vi. Yeah, so Vi is open in A and K, then Zi is closed, so Zi is given by some polynomial, if you like, and so you get these two closed subset, and more or less X is going to be Zi. X is an algebraic set, yeah. So X is going to be more or less Zi union Z1 union Z2. So it's not exactly Z1 union Z2. It will be, you will have to intersect with X, and then it will work out, yeah. So this will give us two reducible components, Z1 intersection X and Z2 intersection. So first claim is that U1 and U2 are contained, U1 is contained in Z2 and U2 is contained in Z1, yeah. So U1 is X minus U2, which is, I'm just doing some set theory, yeah. So X minus V2 intersection X, and that is same as taking X intersection V2 intersection X complement. So if you draw pictures, it would be slightly easier, but anyway, so, and this intersection is just, so taking complement is, you get V2 complement, which is Z2, V2 complement in A2, the AN, that is, and that is Z2, and union X complement. And X intersection X complement is obviously empty. So what you get is X intersection Z2, which of course is contained in Z2. Yeah. So U1 is contained in Z2. And similarly, you will get U2 is contained in Z1. Okay, so U1 is something like this, U2 is something like this, 2 points, and X is made of these two. So, so our candidate for Z2 is something which contains U2, okay? Some closed subset which contains U2, and Z1 is something like this. Okay, so now, so what we get is X is X intersection Z1 union X intersection Z2. Okay, because remember U1 is same as X intersection Z2, and U2 is same as X intersection Z1. Yeah. So we can write it as union of two proper closed subsets. We just have to check that both of them are empty, non-empty, or both of them are proper subsets of X. So meaning X intersection Z1 is properly contained in X, and X intersection Z2 is properly contained in X, and then we are good. Yeah. So but Zi intersection Ui is empty, right? Because Zi is contained in the complement of Ui. Yeah. So that tells you that X intersection Zi is properly contained in X. So that completes the proof that X is irreducible. Okay. Okay, makes sense, everyone? Okay, So I hope it's clear. So now I'll define what an affine space is, affine variety is. So I forgot to write. Okay, so before defining affine variety, maybe I'll write. Okay, maybe first I'll define affine variety. So affine variety is basically an irreducible algebraic set with Zariski topology coming from the subspace topology. Yeah. So definition: an affine variety over a field K is affine variety X over a field K is an irreducible algebraic subset of A and K. Is an irreducible algebraic subset of A and K for some n together with subspace topology. Coming from Zariski topology. On A and K. And this subspace topology is again called Zariski topology on X. Yeah. So for instance, this second picture on the left, this will be a affine variety, and the topology on this affine variety will be the subspace topology. Okay. So it will be closed sets will be we will see that closed sets on this will be points. So I mean, I have drawn real picture, but you should think of it as some sort of complex picture. Yeah. So some algebraically closed. So when we draw pictures, of course, we can draw only real pictures. Yeah. Otherwise, the dimension shoots up. So pictures are a bit deceptive, but you should know what is what are the problems with the picture. Yeah, so this is how people keep track of it. Yeah, so people have pictures in mind, but they also keep track of in what ways the pictures are faulty. Yeah, so that you have the geometric intuition, but you also are careful. Yeah. So, okay. So it's maybe one example you have already seen, this one, and so zero set of x square minus y square plus y cubed, or zero set of this circle x square plus y square minus 1. So one has to argue why these are irreducible, right? So zero set of these things are irreducible. So here is a proposition which will help us, irreducible algebraic set. So here is a proposition which will help us prove this. So let K, so we'll assume K is always algebraically closed. Yeah. So let K be an algebraic be algebraically closed field. Maybe here also K algebraically closed is not important. So here maybe it is important. X in A and K is algebraic subset is irreducible if and only if I of x, the ideal definition of x is, so this is going to be some ideal in kx1 to xn is the prime ideal. Yeah. So once we know this proposition, then of course it's slightly easier to check whether these are irreducible or not. Yeah. So 1 second, let me just. So of course, maybe we will first note that this is indeed the case. So meaning in these examples, these are the ideals, ideal generated. So in the above example, in example 1, in example 1, for instance, we are considering the ideal generated by x square minus y square plus y cube in kxy. So why is this a prime ideal? Or these are prime ideals, these two ideals generated by these two. So how do you decide whether so
you can sort of parameterize by t then something, I mean, some parameter, single parameter.
Yeah, but I mean, how do you check whether it's a prime ideal or not? I mean so it's generated by one element, yeah. And what can you say about this element? X square minus.
If it is irreducible, then it is a prime ideal.
Remember, kxy is a UFD, yeah. It's polynomial ring in two variables over a field, so it's a UFD. So if this is an irreducible polynomial, then it is an irreducible element and hence a prime element. In UFDs, irreducibles are primes. Primes are always irreducible in any integral domain, but in UFD we have this. So you only have to check that these two are irreducible. So so maybe both are sort of equally easy or difficult. So why is the first one irreducible?
No, I mean, or you can check the quotient is a domain, right? So
yeah, but how do you check the quotient is a domain?
Yeah, so quotient is basically k adjoint the variable t and then comma square root of t cube minus t square, right?
Yeah, but I mean that is assuming that this is a prime idea. So you can do all that if yeah, but I mean.
Yeah, then also I have to check why k adjoint t comma square root of t cube minus t square is a domain.
Is a domain, which is same as saying that this is a prime, this is irreducible.
Yeah.
So at the end, you have to check that this is irreducible. That is to check it is a domain is precisely means that this is irreducible. Yeah, the equation defining that field extension is given by this equation. And why is this irreducible? So it is a degree 2 polynomial in X, yeah. So you can, I mean, there are many ways to check. You can use Eisenstein criteria with thinking of it as polynomial in X, and you use no, you can't use Eisenstein criteria with thinking about it as polynomial in. Yeah, you can use. So you take the prime to be y, if you, not y but y plus 1. Yeah. So the constant term has is, you can factor it as y square and y plus 1 for y minus 1. Yeah. So this you can think of it as x square minus y square times y minus 1. Yeah. So consider the base ring to be ky and think of it as a polynomial in X with that as coefficient. Or you can think about it as that this is a degree 3 polynomial, so its square root is not in ky. Yeah. So it doesn't have any root, and hence and then you use Gauss lemma to say. So either way, so there are many Eisenstein criteria. For quadratic, you just have to ensure that it doesn't have a root. Yeah, and it cannot have a root. Square root of y square plus y cube does not belong to ky. Yeah, so that tells you that this is an irreducible polynomial, and similarly, the other polynomial is also irreducible, and hence they generate a prime ideal. Okay, so that. So since they are irreducible, they generate, and hence this is a affine variety. Okay, so so maybe this proposition I'll do next time. Yeah. So okay, so this is not a difficult proposition. It's basically more or less the definition of prime ideal, but and algebraic sets. Yeah, so it's sort of a tautology, but maybe it's time, and you probably have class next. So we will stop here. So are there any questions? Okay, so maybe first I'll stop recording.